Hello, I'm Yanghee Kim, and the co-authors include Sachit Patel, Michael Zoll, and Lichan Yu, and Yulong Wang. Michael is co-presenting with me today. Michael, do you like to say hi to the people?
Yes, hi, here's Michael. I'll present the more detailed analysis that we did while Yanghee gives an overview of the study.
Good, thank you.
Mm-hmm.
So our study was motivated by two recent trends in education. First, collaborative problem solving is an essential skill for children to develop. And second, humanoid sociable robots viewed as a viable tool for child development. So we, the researchers, co-authors, designed an interaction triad of two children working together to help a robot. While the robot being helped, it mediated the two children's collaboration. An issue here was that collaboration is a process rather than an outcome. So we needed to assess collaboration effectively while children performed the task. Also, children's interaction with each other and with a robot were richly multimodal. So the problem of the current study was exploring approach to assessing children's collaborative engagement using a multimodal behavioral data. We had 4 foundational research questions. The first question asks about a child's engagement over time. The second question asks about the agreement among the multimodal sources of data. The third question asks about the relationship of the robot's mediating speech and the child's engagement trend over time. And a fourth question asks about the relationship between two children's engagement trends. Okay, we deployed interaction triads of 2 children and a robot in an ordinary kindergarten classroom. A total of 6 interaction sessions, with each session taking about 15 to 20 minutes. Two children asked to help the robot learn, and about 80 children participated in the study. But for this exploratory data analysis, we included only 2 triads involving 4 children. We collected our data collection include the video recording of the whole sessions, the audio recording of conversations, and a narrative researcher journal. So the second line was great, video recording of facial expressions. So we hope to record their facial expressions, but children were constantly moving around and we didn't have a good data set, so we didn't analyze the facial expressions data. The literature on engagement shows the learner engagement refers to learners' participation in their learning process, and it is a multifaceted phenomenon, including cognitive, emotional, and behavioral engagement. Cognitive engagement refers to ongoing efforts and performance demonstrated by the learners. Emotional engagement refers to learners' emotional states during their performance. Behavioral engagement refers to learners' use of bodily gestures and movements. So we collected 3 sets of multimodal data to measure collaborative engagement. As an indicator of cognitive engagement, we transcribed the children's and then the robot's speech and annotated if their speech was aligned with the others. For emotional engagement, We analyzed vocal information using automatic speech recognition and processing techniques. For behavioral engagement, we annotated children's gestures and bodily movements from video recordings. For data analysis, we took two approaches, the manual and computational. So manual annotations include the kinesics, behavioral engagement, and linguistic alignment. As I said, I know their speech, how their responses aligned with the others. So the table shows, actually, table is covered by images, our own images. So kinesics, for behavioral engagement, we observed the eye contact, children's eye contact, and a bodily orientation, and a gaze on a robot or a peer, and then their gesture use. So if these phenomena are present, we code it as 1, and otherwise 0, non-engaged. So linguistic alignment, we observed children responding to robots' questions, and robots and peers' questions, or extending or elaborating the other's speech. So the segment for annotation was 30 seconds long. For vocal information, we used automatic ASR approach. So the voice research community typically examine vocal intensity and pitch to assess users' and learners' emotional states. So vocal intensity here means a short time energy, and the graphs on the bottom shows what high intensity segment to look like and a low intensity. So high intensity was coded as 1 and low as 0. And vocal pitch was presented like here. Okay, from this slide, Michael is talking.
Thank you. So as Yanghee showed, we have 4 time series which differ in several characteristics. They differ in sampling rates, in variance, and also in units. For example, the sample rate for sound is 144 kilohertz, but for kinesics, it's annotated at 0.5 hertz. In addition, and this is important, they're also unlikely to be in a linear relationship. Now, these type of data, these type of time series actually cannot be appropriately analyzed using traditional correlational measures such as Pearson correlation, and hence we have chosen information theory to analyze these data. Yanghee, do you mind going to the next slide?
Yes.
Thank you. So information theory, I'll just give a very, very brief overview. It treats data with as signals that carry information. And the main construct of information theory to represent correlations between time series is mutual information. And mutual information can take on any value of the time series, and but also can be normalized to range between 0 and 1, 0 representing complete independence and 1 representing complete dependence. And in this study, we in fact normalized mutual information to range between 0 and 1. A quick note on the terminology. We are interested in correlation, but information theory uses different terms. It doesn't use the term correlation, it uses the terms agreement or dependency to denote correlation. And these are specific for information theory. And in this presentation, as well as in the paper, we actually used the terms that are normally used in information theory, but more or less they mean correlation. So the next slide, please. Thank you. So data processing. Before we compute the mutual information on pairs of time series, we transformed the binary data into symbols. This is a common data processing, is a common way to process data for binary data, because it has the advantage of obtaining data which have a higher resolution. Binary data are understood to be only minimally informative, and in addition we are interested in encoding the transitions between segments because we are studying time series. So to do this, triplets of binary data are assigned as symbols, which you can see on the top right side of the slide. For example, triplet 000 is assigned the symbol 1, triplet 001 is assigned the symbol 2. With a symbol length of 3, which is the one we used, there are 9 possible permutations, and hence the symbols ranged from 1 to 9. Sequences of binary data thus become sequences of symbols, and we computed a mutual information on the transformed data. It is important to note that we choose a symbol length of 3 after a series of empirical studies where we started with a symbol length of 2, then of 3, then of 4, and then we choose the symbol length which had the lowest coefficient of variation. It is also important to note that we didn't calculate can you go back, please? Thank you. We didn't compute mutual information on the whole time series, which can have up to 300 segments depending on the length of the session, but on a much smaller section of the time series, and this is called a moving window. The reason is that we want to compute mutual information on behavior that is relatively consistent. We want to obtain mutual information values of 2 behavioral variables where the behavior doesn't vary that much. A window consisting of the whole time series would cancel out any adjustment and fluctuations that participants make over a short time period. Also the window size, and in our study we used a window size of 10 segments or 30 seconds, was determined empirically by testing increasingly larger window sizes and then select the size with the lowest coefficient of variation. Okay. So let's go to the compound variable that we developed. We are not only interested in the agreement between different time series, for example, the intensity and kinesics of one child or a pair of children, but also in their overall engagement. We did preliminary analysis and found that intensity and pitch are highly correlated for each child, while there is almost no correlation between these values and alignment on kinesics. And I will show a slide afterwards on these values. We also found that alignment and kinesics are not very correlated. And to reflect these preliminary findings, we developed a compound variable of engagement, which you can see on this slide. Namely, compound engagement is the sum of behavioral, cognitive, and emotional engagement. But for emotional engagement, we took the average of intensity and pitch. I present now the results of analysis computed on compound engagement as well as individual measures of engagement. And I'd like to emphasize that the aims of these analyses is to explore the potential of our approach to advance the study of engagement. So in this first slide, you see how engagement intended as compound engagement evolved over time for each child and for all sessions. We identified the linear regression line for each child for each sessions, and note that child A and B are in one group and C and D are in another group. The graphs on this slide represent the dynamic trends of compound engagement, showing that child A and B's increased and C and D's decreased. This trend is confirmed by our on-site observations, where we found that child C and D, in child C and D, gradually their engagement increased with the robot and decreased with each other. This is reflected in the graph because collaborative engagement in the sense of linguistic alignment gradually decreased because they gradually interacted with each other less and less, and interacted with the robot more and more. In the next slide, we show the agreement between the different variables which we use to formulate compound engagement. The low correlation between alignment and kinesics, which you can see on the bottom lines of all four figures, means that children either express their engagement through their body or for interacting verbally with their peer or the robot. You can also see in these four graphs that pitch and intensity are highly correlated. This is in the top part of the graphs, which is why we formulated the compound engagement the way I showed you before. Let's go to the last results. This slide shows the agreement between different variables which, the graphs on the right side of the screen show how children's verbal engagement is related to robot talk. We are in fact interested to what degree the robot elicited engagement, and we find moderate to high correlation ranging from 0.62 to 0.68. This means that children were responsive to robot speech. Our analysis allows us also to trace children's engagement with each other over time, and this is shown by the small table on the bottom left. The pair composed of child A and B had a moderate to high engagement of 0.03, while the pair of C and D, the pair of child C and D has a lower engagement. And again, this is reflected in the regressions line that we found, that we showed you at the beginning of the result sections. So this is it from my part.
Okay, from the result, we found the exploratory variable compound engagement enabled us to take multimodal behaviors into account when we assess children's collaborative engagement, also to observe trends over time for each child and compare trends among all involved, and to confirm actually this compound engagement, to confirm the engagement that changes dynamically over time. And collectively together, compound engagement enabled a more authentic assessment of engagement behavior of children. And more important, we found that the quantitative result compound engagement was consistent with our narrative research notes. Both quantitative and qualitative methods worked complementarily to provide us with a rich account of children's collaborative engagement. And we explored the use of mutual information to synthesize the multimodal data set. Now we found it was such a powerful tool to synchronize and analyze multimodal data, sources of data. And there was a weakness in our analysis of vocal data in this in this paper. And we used the training data instead of the baseline data for each child. So in the future, we'll expand the analysis to all participating children and confirm our compound engagement. And also using individuals' baseline data to analyze their vocal information. Thank you. Any questions? And then you can visit our website, the research site, createresearch.net.